guys, this is Professor Janacek, and I want to go over a few more examples of finding derivatives using the product rule and the quotient rule. Here we have example number 6. We've got d dx of x e to the 5x. Well, looks like we have two functions, an x and e to the 5x, and those are being multiplied together. So again, x is our first function and e to the 5x is our second function. So according to the product rule, we will take the derivative of the first. Well, remember the first one is x, the derivative is just 1, times the second, which is e to the 5x, plus the first, again that's just x, times the derivative of the second. Okay, so we need to take the derivative of e to the 5x. Let's just make sure we remember how to do this because it will require the chain rule. So taking the derivative of e to the 5x, well, the derivative of e is just e to some, the derivative of e to some power is simply e raised to that power, but the chain rule says I have to take the derivative of whatever's in that exponent. So in this case we get e to the 5x times the derivative of 5x is simply 5. So it ends up being 5e to the 5x. All right, so that is 5e to the 5x. Now we can clean this up just a little bit. That's e to the 5x plus, let me put that coefficient in front, 5x e to the 5x. And there we go for that one. Example 7, we're taking the derivative of 4x e to the x over x squared plus 1. Now I definitely see the big thing going on here is that I've got a quotient, but notice inside this quotient I have a product there in the numerator. All right, so how do we do this? Again, big picture is that it's a quotient. According to the quotient rule, I'll take the derivative of the numerator. So that's where we're going to start. I'm going to take the derivative of this numerator, but notice the numerator, that's a product. So here I've got to use the product rule inside the quotient rule. According to my product rule, I've got 4x as my first function and e to the x as my second function. So product rule says we'll take the derivative of the first, well again that first piece is 4x, the derivative is just 4, times the second, which is e to the x, plus the first, which is 4x, times the derivative of the second, well the derivative of e to the x is just e to the x. All right, that was just the derivative of the first, of the numerator. Now I'm going to multiply this times the denominator, again going back to my quotient rule, derivative of the numerator times the denominator, minus, now I'm going to take the numerator times the derivative of the denominator. Well, the derivative of that denominator is simply 2x. And all of this is over x squared plus 1 squared. All right, we've got all the derivations done. Let's see if we can simplify this. In the numerator, we have 4e to the x plus 4x e to the x times x squared plus 1 minus, that ends up being 8x squared e to the x. This is still over x squared plus 1 squared. Again, I'm not actually going to multiply that out because at the end I may need to reduce and I want to leave it in that factored form. All right, well let's go ahead and multiply those two binomials, see what we get. That gives us 4x squared e to the x plus 4x cubed e to the x. Again, you can multiply this in any order. Plus 4e to the x plus 4x e to the x minus 8x squared e to the x. Again, all over x squared plus 1 squared. Just take your time with that multiplication. Let's go ahead and combine some terms. I notice that I can combine the 4x squared e to the x and the negative x squared e to the x. At the same time, I'm also going to go ahead and write this in descending order. So I'll start with the highest power first. So 4x cubed e to the x comes first. The x squared terms will come next. I'll go ahead and combine the 4 and the negative 8, gives us negative 4x squared e to the x. then the x term, 4x e to the x, and finally the one that has a constant in front of that e to the x. All of this is still over x squared plus 1 squared. All right, well, I don't think I can combine anything else, but I do notice that in the numerator, everything has a 4 as well as an e to the x. So let's go ahead and factor that out, 4e to the x. Oftentimes it's considered a little easier to read this way. If I factor out 4e to the x, we end up with x cubed minus x squared plus x plus 1. And of course this is still over x squared plus 1, quantity squared, and if we could factor this anymore we would, but this does not factor, so that is as far as we can go. Nothing reduces. That is it. All right, let me move these down just a bit. Have a little more room here. Okay. Now let's try to find the derivative of 9 over x to the 5th. Yes, I know you can write this as (9x to the negative 5th) and then take the derivative using the power rule, but I want to just exemplify the quotient rule again. So I'll treat 9 as the first one and x to the 5th as the second function. So again, yes, you could use the power rule, but I just want to give you a little more practice using the quotient rule. So again, the quotient rule says take the derivative of the numerator. Well, that's just 0 times the denominator, x to the 5th, minus the numerator times the derivative of the denominator. Well, the derivative of x to the 5th is 5x to the 4th using the power rule there. All of this is over the denominator squared. If we clean this up a bit, that first term ends up being 0. We don't need to write that down. Second term is negative 45x to the 4th. In the denominator, x to the 5th raised to the 2nd power is actually x to the 10th. Oh, and now we can reduce those x's. That gives us negative 45 over x to the 6th. And there we go. All right, let's also see if we can use the quotient rule here on this last example, number 9, d dt of 3t to the 16th minus 4 over t to the 6th. Well, again, there are a couple of ways of doing this. I want to go ahead and treat this like a quotient, though. That's what it looks like. My numerator is my first function, 3t to the 16th minus 4. My denominator, t to the 6th, that's my second function. So, to begin with, we start by taking the derivative of the numerator. Well, in the numerator, the derivative of 3t to the 16th, that is, what, 48t to the 15th? And the derivative of 4 is just 0. So we take that, we multiply it by the denominator minus the first one, the numerator, 3t to the 16th minus 4, times the derivative of the denominator. Well, the derivative of t to the 6th is 6t to the 5th. And all of this is over that denominator squared. Well, we can clean this up a bit. That gives us 48t to the 21st minus, now here I'm going to go ahead and multiply these, distribute that 6t to the 5th along with distributing that negative. So that gives us minus 18t to the 21st plus, watch those positives and negatives, 24t to the 5th. This is over t to the 6th raised to the 2nd power is t to the 12th. So now we have, oh, I can combine some things. That t to the 21 for those first two terms, that gives us, oh, that gives us 30t to the 21st plus 24t to the 5th over t to the 12th. All right, now we can go ahead and break this up into two fractions. 30t to the 21st over t to the 12th plus 24t to the 5th over t to the 12th. And now we can reduce those t's. We end up with 30t to the 9th plus 24t to the negative 7th. There you go. Not too bad. I do want to mention that this one, again, we could have used the power rule on this. I could have started by breaking this apart to two fractions, sort of like the last step I did when I worked it first. This is 3t to the 16th over t to the 6th minus 4 over t to the 6th. And those can be rewritten as 3t to the 10th minus 4t to the negative 6th. And now if we use the power rule, just the power rule, we end up with 30t to the 9th plus 24t to the negative 7th, which is exactly what we got before. So there you go. Either way, it works. Enjoy.